As an aspiring physicist, I am in love with studying the deepest, most extraordinary ideas that nature has to offer and that have kept humans busy for a long time. Even though nature is always one step ahead of us, it often leaves remarkable hints of the truth along the way. Today, I would like to tell you a story, not only about my thesis, but about how one of the secrets of the early born universe can be explored by looking at the smallest things around us. Since the dawn of humanity, we have questioned, what are the fundamental indivisible blocks that make up everything in the universe? You've probably learned that everything is built from atoms, which are in turn made of electrons and protons. However, even though electrons are fundamental particles, the protons are not. In fact, the proton is made up of many point-like objects, like quarks and gluons, which are called partons. Therefore, our best picture of a proton is not one of a marble, but a bag with a great number of these fundamental marbles. But how come we never heard about or seen such partons if they are in fact the fundamental particles? That's because all partons interact with each other via the strong force, which makes them obey a very important rule. No one leaves the bag. This explains why they are never seen just by themselves. But still, how do we know that they exist in the first place? Are they always that obedient? Imagine two protons going towards each other at near the speed of light. What do you think will happen when they collide? Well, at the moment of impact, the protons will completely break apart, and the partons that were previously confined will then become free and leave the bags. These free partons will collectively build a new state of matter, the quark-gluon plasma. This medium is incredibly fascinating, as it was responsible for filling the universe when just a femtosecond had passed from the Big Bang. So, we would obviously like to study its properties. The problem is that the medium can only last for a fraction of a second before the strong force forces the partons to go back into bags once again. Thankfully, we can still see its effects, as there are faster, more disobedient partons that manage to escape the medium altogether. By looking at how these particles were affected by their passage through the QGP, we can actually study the medium. These types of collisions are recreated at the Large Hadron Collider, although instead of protons, they use nuclei of lead. This would be the equivalent of substituting each proton in the previous collision by 208 protons. Obviously, the final result of such a monumental interaction is a fantastic firework of particles and a much bigger QGP. These little bangs are known as heavy ion collisions. In the next few years, the LHC will start to run heavy ion collisions with lighter nuclei than lead, which will allow us to generate more collisions than ever before. This means new physics on the horizon. However, Monte Carlo simulators of such collisions seem to give unreliable results for these upcoming experiments. This is where my thesis comes in. I will try to change the current heavy ion collision simulators in order to make them more suitable for lighter collisions and study the measurable effect of the QGP in these lighter systems. Thank you for watching.